Hello everybody and welcome back to episode 9 of my video series in which we program a video game, an entire video game from scratch, from beginning to end in the C programming language. Last time we left off, what we were doing is we talked a lot about timekeeping in Windows, and I think today we're probably going to continue with our little timekeeping experiment here and trying to get an accurate FPS out of this game. But before we get started, I should probably talk a little about some of the comments that I received since last time. So one viewer commented about he is wondering why we are using the Win32 platform instead of UWP, which stands for Universal Windows Platform, the latter being way more modern. It's obvious that you didn't go with .NET based platforms since they require annoying dependencies, but I was wondering what led you to the choice of Win32. Well, yeah, you're right. I didn't choose .NET for obvious reasons. UWP I feel like UWP is just another layer of abstraction between us and the operating system that we don't need. Yeah, UWP is definitely it's definitely more modern. I think it was invented in like Windows 8 for the Windows Store apps, and it's sort of a, I don't know, part of the reason why it was invented, I think, was to facilitate the sandboxing of those Windows Store apps, so that they can't really interact or interfere with the rest of the operating system. For example, I think UWP apps only have access to like the virtualized parts of the file system and registry and things like this, so they can't read data that normal Win32 applications would be able to read, or they wouldn't be able to collect data about your computer that other Win32 applications would be able to collect unless you gave them special permissions. And again, it's just a sandboxing technique. I think this works really well for things like mobile phones. You know, Microsoft had a mobile OS for a while, and I thought that OS was pretty good. But anyway, it works good for things like that where the apps need to be highly containerized. Also, obviously, this works well for the Xbox, because the Xbox, each game needs to be highly containerized so that it can't interfere with the operating system of the Xbox. It can't interfere with other applications on the Xbox, things like this. There's more to it than that. There's other reasons why you might want to use UWP other than that. Namely, if you want access to like the Windows Store, you have to use it. And if we want to port this to Xbox, we have to use it. So we may actually revisit this one day if we want to make this game compatible with the Xbox. We would have to use UWP. But let me just look it up here. UWP versus Win32. Alright, choose your app platform. When you want to create a new desktop app for Windows PCs, the first decision you make is which application platform to use, etc., etc. And then, alright, so UWP this platform provides common type system APIs and app model for all devices that run Windows 10. UWP applications can be either native or managed. Meanwhile, and we'll just skip WPF, let's pretend that doesn't exist. Win32, this is the original platform for native C and C++. And I mean, this says it all. Windows apps that require direct access to Windows and hardware. This makes the Win32 API the platform of choice for applications that need the highest level of performance and direct access to system hardware. So highest level of performance is all you have to say, and I'm on board. So that's why I chose it. So let's see, what other comments did we have? Another commenter asks about emphasis on debugging so far this video, which honestly there hasn't been much, but there will be more emphasis on debugging when we get to that point, which is probably coming up pretty soon. Yeah, let's see. He's a CS student, mainly focused on C and C++. What resources would you recommend to learn how to debug code better? This is a question that I'm not really prepared to answer right now. I'll come back to it later, but I don't know that there are any really good resources publicly available that are specifically geared toward debugging. So my job at Microsoft is as a debugger, and I spend a lot of time debugging other people's code that I did not write. And writing code versus debugging code is sort of like the difference between being a copy editor, someone who just goes through someone else's writing and correcting their punctuation and grammar mistakes and things like this, being like, oh hey, I think this sentence should go at the end of the paragraph, etc. Versus being an author where you're actually creating a whole new story. That's my sort of like go-to analogy for the difference between a developer and a debugger. And obviously there's a Venn diagram of overlap of skill sets between a developer and a debugger. Obviously a developer has to know how to do some debugging, and a debugger has to be able to know how to do some programming. But they're two separate skill sets with a bit of an overlap. So anyway, there's obviously you can go on the internet and watch hours and hours and hours of programming tutorials and learn how to program, but there isn't a whole lot of stuff out there that is specific to debugging. And again, this is tooting my own horn because it's what I do. It's what I do at work, and I'm basically I think very highly of debugging because I think it was Dennis Ritchie maybe who wrote the C programming language. He has a famous quote that, well, I'll paraphrase because I don't remember the exact quote, but essentially he says that if you write the cleverest code that you can possibly write, then you are not clever enough to debug that same code, because debugging code takes even more cleverness than it did to write the code in the first place. So what I take from that, and the mantra that I hope that you see come through in my code, and what I hope that you come away with is, I actually prefer writing boring code, right? Very boring, predictable code that is not clever. Because when you write boring code, it basically makes it very easy to debug, it makes it very easy to read, it makes it very easy to predict what it will do and what it's supposed to do. So, writing clever code is fun if you're in sort of like a code golf competition or a hackathon or something like this. But yeah, for day-to-day use, if you want something to be, if you want your code to be like production quality, run something that runs for 10, 20 years and just no one ever has to question it because it just runs perfectly and is rock solid for its entire life. It should be boring code. It shouldn't be too clever. Anyway, so back to the debugging learning material. I was actually talking to a coworker about this last week, and he mentioned actually wanting to get into the video stream or video recording scene, just like I'm doing, except more from a debugging standpoint. And he's even better at debugging than me. So if he ever starts doing that in a way that is like, publicly accessible, like on YouTube, I will definitely promote his channel. Internally at Microsoft, we have so much awesome debugging tutorial, debugging content, video, wikis, all this kind of stuff that it would blow your mind, but it's all internal stuff that I can't share. So yeah, so coming up with publicly accessible content that is geared specifically toward debugging is definitely something that I'm interested in. I want to see that come to fruition. So check back later, and we could definitely come up with some. We might definitely be able to come up with something. Anyway, so let's get on to some actual programming now. If you remember correctly, if you remember from what we did last time, where we're in WinMain right now, we called query performance frequency to get our perf frequency, and remember, this only needs to be called once because this perf frequency value is only is set once at boot and is never changed. So you only need to call it once. And now down here in our while loop that represents each frame, we use query performance counter to start the counter. We do all of our stuff, and then we call it again to mark the end of all of our stuff. And then we we calculate the difference between the start and the end, and that's how long the frame took. And knowing that, we can calculate frames per second and all this kind of stuff. Let's see, what do I want to do first? Okay, first thing I want to do is I actually do want to get rid of these large integer unions, just because it's an N64, so that's what I'm going to use, N64. That way I'm consistently using these data types from the standard int header file. What? Yeah, okay. Let's see, Visual Studio. Visual Studio is going to Visual Studio. Alright, we're going to... Oh, and you know what? I'm going to take these out too, because frame start and frame end, I don't think that those need to be global variables. I think that those can be local variables that are inside the WinMain function where our loop is. So there's no reason to have them here. Yeah, general rule of thumb is don't be afraid to use global variables when you need to, but at the same time, you should try to not have more global variables than is necessary. The reason why sometimes global variables are frowned upon, especially for students and people who are just starting out with programming, global variables are often frowned upon because since they can be accessed from anywhere by any thread in your program, it just basically makes the opportunity to make mistakes much bigger. You could be updating the wrong variable from the wrong function, and the compiler wouldn't even warn you because it's a perfectly valid thing to do because the variable is global. That kind of thing. So let's see. Per frequency elapsed to microseconds per frame. All right, let's see. Raw frames. Maybe I should make... Okay. Now, I know that earlier I said I'd like to be verbose with my variable names, but there only up to a point. Only up to a point. Sometimes abbreviations are okay. So I'm going to abbreviate. And you know what? You can actually, I'm not going to do this, but you can actually do this. Where's the micro symbol? Maybe I'll just type it. Micro. No. There it is. There it is. Elapsed microseconds per frame. That's perfectly fine to do with Visual Studio. It supports, Unicode characters. You can put Unicode characters in your variable names if you want to, but I'm not going to do that. Elapsed microseconds per frame. All right, now let's go back to main.c and correct all of the stuff that we broke. So I need two more variables here in my when main function, and we'll call them int64 frame start, int64 frame end, and this message variable, I'm going to put it up here at the very top too. Now, actually, I believe it was in, I don't remember, but like the oldest standard of C, you had to put all of your variables up at the very top of your function. Notice how I had this variable down here at the very bottom, or in the middle of the function. In the oldest, one of the oldest C standards, that was actually illegal and you couldn't do it. The compiler wouldn't let you do it. You had to put all your variables, all of your local variables, right at the very top of the function. Even though you don't have to do that anymore, you can declare variables in the middle of a function if you want to. I still find it to be a good practice. It's still a good idea, and one of the biggest reasons why is because this programming pattern where you do something, and if that something fails, then you have a goto, and then the goto exit goes all the way down to the bottom of the function. Now, in the bottom of the function is where you usually have your cleanup code, and we'll say every thing that you allocated inside that function, you'll then free it or deallocate it here in this little exit clause, this little, I don't know what you want to call it, this little cleanup or exit, bit of your code, this region at the very end of your function. Anyway, so what can happen, and what can still happen, even in the newer C standards that we're using now, that you, let's say, go up here, and let's say you failed. Let's say you failed right here, but you declared some variable right here, and then this thing never got declared. And then you go down here to your exit area, and your exit stuff tries to free it, and you end up trying to use or reference a variable that you haven't even declared yet. That can definitely be a thing, and I could probably demonstrate it for you, but I think you get the idea. That's why if I can put all of my variables at the top, at the very beginning of a function, it's best to go ahead and do so. The other thing that is good about, the other thing that makes this a good practice is putting your variables at the top of the function, is that if you're going to have your functions, basically shouldn't be too big. Your functions should be pretty small. Your functions usually should be designed to do like as few things as possible, and to just do those few one or two things and do them really well. So if you find yourself, writing just like gigantic functions and, declaring variables in the middle of those functions, is usually something that it comes with the territory of writing huge functions. It's not a good programming habit to get into. So, all right. Okay, so now I can correct this since it's no longer part of that global data structure. I can correct this, and correct that. There we go. And since I changed elapsed microseconds per frame from a large integer union to just a regular 64-bit integer, that means I no longer need this quad part. I no longer need this dot quad part piece. So I'll remove it. I'll remove it. Oh, I can remove that. I can remove that. And that. Remove that. Remove that. This may actually not be. I'll leave it. I'll leave it in there. The perf frequency. I'm trying to think if there's anywhere else in the program where I ever might need to reference that, and I could. Yes, there is. I can imagine needing to time something else that's outside of the scope of this function. So this being a global variable is probably a good idea. And notice that the work that we just did had the nice positive side effect of making our code much cleaner, so it doesn't, scroll off the end of the screen here. So I like it. All right, let's fix our little okay, and then microseconds. Okay, I'm going to make an int 64. Okay, elapsed microseconds per frame accumulator. Let's see if that works. Okay, so every time we get done rendering a frame, I'm going to add to elapsed microseconds accumulator. I'm going to add to it the elapsed microseconds per frame. I don't think that needs to be global either, to be honest with you. I don't think that needs to be global either. So I'm going to take it out. Alright, back up here. There we go. Elapsed microseconds per frame. Okay, and then every 100 frames, we are going to reset the accumulator. Elapsed microseconds per frame accumulator equals 0. And this is where we're going to calculate our averages. Delete this. Okay. So int 64 average microseconds per frame equals elapsed microseconds per frame accumulator divided by calculate average FPS every that many frames. So our average. All right, how do we turn this into frames per second? We should do. Hang on a second. Okay, I may not need this variable, but I'm going to just calculate. I'm just going to convert it into milliseconds. And probably more like. Okay, now float is the data type that we use to represent decimals, or use fractional or decimal numbers. So far, we've only been dealing with whole integers, but this is going to be the data type that we use for decimals. There's also a double data type, and a double is essentially just twice as big as a float. If you need to express like a really big decimal, like 3.1415926 something, I can't forget the rest of the numbers, but it's 64 bits long. But you shouldn't use data types that are bigger than you have to, right? We're going to do average microseconds per frame times 0.001f. Okay, I think that will do it. I'm going to run to cursor. Alright, let's see what my locals are here. Now the average microseconds per frame is 2,786. I'll take one step here. Oh, I pressed the wrong step. There we go. Which makes our average milliseconds per frame 2.786 milliseconds. That sounds about right. Alright, I think that's about right. Alright, let's see. We can get rid of this now. Average. We'll do average milliseconds per frame is O2F. Is that how you do it? 2F. I think so. I think it's like 0.02F or something. Basically, I'm trying to think of the format specifier to tell printf that, hey, I want you to format this number with only 2 decimal places. Never go more than 2 decimal places. And then instead of average milliseconds per frame, we don't need that variable per se, because we can just calculate it ourselves right here. And delete that. Alright, let's see how it looks now. Where is my output? There we go. Average milliseconds per frame. It's about 2 milliseconds per frame, which is pretty nice. It's pretty fast, huh? Let's clear up these warnings. Using operator storing a 4-byte value and then casting the result. Cast the value to the wider type before calling. What are you talking about? I'm not using the multiplication operator. And this is not a 4-byte value. That's not a 4-byte value. That's probably a 4-byte value. Incompatible types. From int64 to large integer. I don't think so. Because we looked at this last time, right? Large integer. Yeah, we looked this up last time. It's a 64-bit, a signed 64-bit integer. It's a D word plus a long. I'll just use the cast to get rid of the warning, and code is still working perfectly fine. And also notice if I go down to where if I go down to render frame graphics, and let's see, render frame graphics, which is right down here. This is like the only thing I'm doing, this for loop where I paint the entire screen blue. This is pretty much the only thing that I'm doing that costs us any CPU cycles. So if I comment that out and run the game again, what's going to happen this time is that I just have my bare back buffer that I haven't drawn anything to. But look at my frames per second, or my time elapsed per frame has gone down to less than a millisecond per frame. So that's pretty awesome. So using these timers, we can now basically profile our actions. And profiling is a very important part of programming. Anytime you want to measure how fast something is, we call it profiling. You want to benchmark it and see how fast your stuff is, and you want to keep an eye on how long it's taking you to draw each individual frame, because obviously we can never go over that 16 millisecond budget, because that would put us at less than 60 frames per second, and we never want that to happen. And then secondly, this is how you get a feel for how efficiently you're writing things. So we may get to a point in our game where if we're drawing everything on the screen, it may actually take too long. But if we come up with some really clever algorithm that only draws parts of the screen that have changed since the last frame, that would make it take much less time to draw each frame. So we may end up implementing something like that. Would be really awesome, actually. And that's what Windows already does, actually, by the way, is it has this whole concept of invalidating particular rectangles. And so if you have a window, like let's say calc.exe, so you're using calculator.exe and you start typing numbers into it, well, when you do that, Windows knows that the only thing that needs to be repainted is like this little window right here around the number, and this little bit right here that is updating dynamically. But it doesn't have to redraw all these buttons every single time, because these buttons don't change every time you update a number. Well, actually they do. They flash every time I press a number on the keypad. But you get the idea. The buttons that don't change, I don't have to ever like redraw those unless something happens that actually modifies them. And that's that Windows achieves that by actually programmatically only invalidating a particular like subsection of the window, so it doesn't have to repaint the entire window. Oh, and by the way, that is something that I wanted to bring up here. and since we're talking about drawing graphics, this is a good time to do it. I'm going to bring that back into play. And what we're doing right now, where we are drawing the entire screen, every single frame, in our game loop right here, is actually not the way that you would do this if you were programming a normal Windows app. So if you go and set out to program like a Win32 application, please don't think that what we're doing right here, is the correct way to be drawing those graphics, because it's not. What we're doing right here is redrawing the entire screen, every single frame, which you don't want to do if you're just making a Win32 app. What you're supposed to do if you're just making a regular Win32 app is, in your window procedure, you're supposed to be handling these WM Paint window messages. And because Windows, every time it detects that a piece of your window needs to be repainted, it will send you these WM Paint messages. And that includes things like when you maximize the window, when you minimize the window. It sends you these WM Paint messages, and then you can respond and do part of you can then draw your graphics as needed at that time. That's much more efficient, because you don't have to sit there, and your app won't be sitting there redrawing its GUI every single frame. It's just going to be doing it it's going to be reacting to these WM Paint window messages. So we don't need these because of the type of game that we're making, but just know that if you were making a regular app, you would want to be drawing your graphics totally differently. Like for example, if you have your app is, let's get two instances of calc.exe here. Let's say I've got the two windows overlapped here. None of the part of the calculator that's on the bottom, none of that is getting redrawn right now, because my mouse is over it. And let's not take into account things like translucent windows. Let's pretend like these are two completely opaque windows. So there's no like alpha blending, there's no compositing, there's no anything like that. So if I move this one out of the way, then this one needs to be redrawn, right? So otherwise, if you did it the way that we're drawing graphics, if you drew graphics the way that we're doing it for this game, your app would be back here in the background, still drawing constantly, drawing way more pixels than it actually needed to. Alright, so hopefully that was somewhat explanatory. Let's see, what else needs to be explained? Oh, there is one other thing I wanted to talk about, and that is our back buffer. When we allocated the memory for our back buffer using virtual alloc, you notice that I never free this memory. And the reason I never free this memory is because I don't need to. If you are in a user mode program and you allocate memory that you plan to have available for the entire lifetime of the program, then it doesn't matter if you never free it or not. So for example, if I go down here to the very end of my program, virtual free, and then I could supply my memory, but I don't have to do that. It's not necessary. Windows will automatically clean that up for you when your process exits. So there's no need to free that manually. Now, on the other hand, if you are allocating some memory that you intend to be like short-lived, which is something else that we'll be doing soon once we start loading in sprites and things, and we'll have sprites and tile maps and things that get switched in and out. Well, that's a completely different story. In that case, you have to be very careful to free the memory that you allocated, or else you'll start leaking. So let's see, what else? All right, I think that's all I want to talk about for now. Let's finish out this, try to get the rest of these errors taken care of. Okay, and again, the only reason this works is because both large integer and int64, they're both the exact same size. Okay. What else? Oh, sorry. Here is another warning that is, okay, int underscore snf printf underscore s, all this, function not inline. So that's something else that I need to talk about, is what does that mean? What does inlined mean? Inlined is basically when you have a function that you want to perform as fast as possible, and the function is pretty small and you just want it to happen really fast. What the compiler will do for you is actually go and get a copy of that function, bring it back to your current function, and literally just copy paste it in line with the rest of your function. The point being, or the reason being, is that calling functions is costly. It costs CPU time. It costs memory accesses. You have to push things to the stack. You have to, reconfigure the stack before you can call another function. That function has to run, and then that function has to restore the stack to its previous state. Those stack operations cost time. They cost microseconds. They cost CPU cycles. So to avoid them, we can actually inline the function so that it looks like, in your code, it looks like a separate function. It reads like a separate function, but what the compiler can do for you is inline it while it's compiling. It just takes a copy of that function and pastes it inline into your function. So when I'm not inlining a function, I am incurring that slight performance penalty of a function call. That being said, I can't do anything about snprintf, so I'm probably going to end up just disabling that warning, because at this point, basically, I trust the compiler on what to inline and what not to inline. There are ways, just like I've been able to overrule a lot of these other settings. Like, for example, I could control the padding in my data structure using that pragma pack compiler precompiler directive. You can do the same thing with function inlining. There's like a force inline keyword or whatever. Yeah, force inline keyword, or I think there's another one that's like always inline, and it's like, no, really, I really want you to inline this. Things like this that you can do to force the compiler to inline your function no matter what. The downside of inlining is that it creates a larger executable, basically, because you are creating multiple copies of your function. If your function A calls function B, but function B is inlined inside of function A, then function A becomes larger because now it has a copy of function B inside of it. Make sense? So that's why you might and might not want to inline functions. But for now, like I said, I'm just going to trust that the compiler knows what to inline and what not to inline. I'm just going to trust the compiler for right now. Later on, if we get into want to do more performance tuning, we may experiment with more inlining our own functions, but for now, not so much. Disable warning about function not inlined. Okay. 4710. It's still 4710. Primary disable. Huh. Maybe I need to put it in the C file. Now will you stop complaining? No. So I think we might actually have another Visual Studio bug here, where it literally just isn't going to listen to me. I'm telling it to disable this warning 4710, and it just won't do it. And now the other warning has gone away without us doing anything, but this warning, the one that actually shouldn't be here, is still here. So I'm thinking it's probably a Visual Studio bug at this point, which, you know, it's not a big surprise. All right, let's take care of this one. Arithmetic Overflow. Okay, what is overflowing here? It's 64. What if that would be silly if that worked? Yeah, that's not gonna work. That's stupid. Alright, I'll have to play with this and see why it won't go away. But anyway. Let's see. Okay. Tab FPS. How do I calculate average FPS? Average FPS. Okay, we need to make this a we need to make this a float, and we need this to be 1 decimal place. Oh. 1 over, let's see, elapsed microseconds per frame. Divided by 60 times something like 1, 2, 3, 5. Okay, let's try that. Okay, so I think that is correct. I think that is our FPS right there, about 300 FPS. Okay. Let's go back down to render frame graphics. It's interesting how slow this is. I still just can't get over how slow this is. If I run it without that, let's see what happens. Yeah. Now it's more like 2500 to 3000 FPS. Okay. Alright, I'm going to make another pound define. We're going to call it target microseconds per frame, and it's going to be 16667. So 16,666 microseconds is 16.667 milliseconds, which is precisely 60 times per second. So there's one other thing is this where we are writing it out to output debug string, and we're writing it out to the debugger. That is fine, except every time the game runs, like I can't really keep an eye on this FPS counter and look at the game at the same time because the game is full screen. So I think eventually we will probably ditch this output debug string stuff altogether. And once we have gotten to the point where we can draw text on our video game screen, we'll probably just write our debug information right here on top of the video game itself. So that way we don't need Visual Studio at all. We don't need to look at Visual Studio at all when our game is running. Oh, that's why it's so slow. It's because I'm sleeping, huh? Okay. Yeah. What if I change that back to sleep 0? Let's see how many FPS I get now. Oh, never mind. Still getting a very similar value. Okay, let's see. We need to figure out how long to sleep. Or actually, I don't know. This is where it gets really hard. Okay. I'm going to try to accomplish this without calling time begin period 1 like this. This function right here messes with that global system timer that we talked about at great length last time, and it attempts to set the global system timer resolution to 1 millisecond. And it would be easy if we did that, but the problem is, Microsoft has been recommending to people to never call that ever anyway, and to basically not mess with the global system timer resolution, because it's a global resource and it affects it affects the operation of the entire machine, of the entire operating system. And if your timer resolution is set to a very small value, it can actually have the counterintuitive effect of reducing performance on your machines because your threads are are context switching so much more often, and your threads are getting preempted so much more often. You end up spending more time context switching than you do actually getting work done. So we are going to try to not do that. And the other reason why we should try to do this without modifying the global system timer is because I don't know if it's going to work or not. Like I said, this is only like, it might not be able to set it to 1 millisecond. Different hardware platforms have different timer resolutions. Some of them might be able to set 0.5 milliseconds lowest minimum resolution. Some of them might be able to set 1 millisecond lowest resolution. And some hardware platforms may even be less than that. So I don't think that using time begin period, I don't think I can use that to guarantee 1 millisecond timer resolution. So I'm going to try to do it without messing with the timer resolution at all. And I think what that means I'm going to have to do is I'm going to have to, while elapsed microseconds per frame, while it is less than our target microseconds per frame, we'll do something like this. We are going to yield the rest of our time slice to another thread, and then we are going to call this again. We're going to call query performance counter again, and hold on. Okay, this is all still good. This needs to go, I think this needs to go up here. Total frames rendered. Okay. Oh yeah, we need to recalculate this every time, don't we? We need to recalculate elapsed microseconds per frame every time through this loop. There we go. There we go. Okay, I think this is going to work. And now we can do, hold on. Let me look at my, okay, gperf data dot raw FPS average equals, or raw FPS average equals this mess right here, and our g performance data dot cooked FPS average equals something we'll get to in a second. Okay, hang on. And oh yeah, we need an accumulator for, no we don't. Yes we do. We need another accumulator. Int 64 microseconds per frame accumulator cooked equals 0. Raw. Those variable names are out of hand. Probably going to rename those. Okay, and then after this, we're going to okay, so after we've done our sleep, elapsed microseconds per frame, accumulator cooked is going to be, we're going to do that. Okay, so we're basically taking measurements after we have drawn our frame. We're going to take a measurement and we'll say it took us 2 milliseconds to draw this frame. Then we're going to go to sleep and we're going to spin in this loop right here until we have slept for the required amount of time, which will be about 16 milliseconds, at which point we will exit the loop and we're going to have another measurement, which is going to be our basically the elapsed amount of time, including the amount of time that we slept, which should work out to about 60 frames per second because of this guy. So int 64 average microseconds per frame cooked equals cooked divided by calculate average FPS every number of frames. Okay, so there's our raw FPS average. Our cooked FPS average will be calculated the same way, only it will be using the cooked accumulator instead of the raw accumulator. And finally, in here, we can just do gperf data dot. Let's do cooked. Okay. And then we'll do average FPS cooked. And then we'll do average FPS raw. Percent 0.01F. Are we ready to go? Is it going to work? Only after we fix these compiler errors. Both accumulators need to be reset to 0 here. Okay. We are racking up these compiler warnings that we're going to have to try to fix at some point. Let's just see what happens. Okay, definitely messed up. We are definitely messed up here. Oh. Okay, the reason that happened, I think, is because we actually went more than our buffer would allow, and that's why it got truncated. This is why our new line character, it got truncated, and this is why everything is on one line now, because our buffer wasn't big enough. Let's try it again with a bigger buffer, and we'll just see what happens. Oh, I made another mistake here. Average milliseconds per frame is what? What was our average? Average microseconds per frame. Okay. Yeah, that's a pretty big mistake there. Whenever you have 3 format specifiers, you need to make sure you have 3 variables in here to go in place of every one of those format specifiers. That's also a common problem that C has that the compiler didn't tell me about. Even though I have all warnings enabled and I have code analysis, like especially, I don't know why static code analysis could not have told me um, that I didn't have a matching number of format specifiers and variables to uh, stuff into those placeholders. I don't know. But let's see what happens now. No, it's still messed up. Huh. I wonder what is going wrong. Let's run to cursor and see what happens. Okay, look at our local variables. We have average microseconds per frame cooked, 17 milliseconds, which I guess is okay. It's within 1 millisecond. Average microseconds per frame raw, which is what we expected. We have elapsed microseconds per frame. The accumulators, those look correct. I don't know if these are correct or not. They might be. They probably are. So, yeah, they must be correct. So why is this not working? What is ngperf data? G performance data. Total frames rendered 100. Raw FPS average 246. Cooked FPS average 35. Per frequency, everything looks normal. I don't understand why this isn't working. Okay. Average FPS cooked is... Oh. 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 Okay. It's because these are the wrong data types. FPS needs to be a float, doesn't it? Cooked FPS needs to be a float, doesn't it? Now let's try and see what happens. Now everything's working perfectly. No, it's still not working perfectly. Average milliseconds per frame, raw. Our FPS is looking better. We're sleeping too long though. It's nowhere near 60 FPS. Either that or I'm doing the math wrong. We'll figure it out. Okay, well, we are way over time, so I'm going to have to stop here. And we almost got there. We're at a point where we are achieving a somewhat predictable FPS. I mean, we're going to get this closer to 60 FPS, but as it is right now, it's not all that. It's not terrible because that means we're achieving a steady, consistent FPS, even though it's in the 30s right now. But that's really good. I mean, that would be a playable game. But anyway, we're gonna get that up to 60. Let's see what else. Yeah, so that's all the time we have, and we're definitely going to have this fixed by next time, but we did make some progress. Anyway, as always, thank you for watching. If you have any comments, please let me know. You can write them, your comments on this video, on YouTube. You can also find me on Twitter at Joseph Ryan Reese, and like and subscribe, and we're going to make an awesome video game. So until next time, I'll see you. Bye.